So, welcome to this session. So, in our previous session we discussed about the basic parameters and basic concepts of our transmission line, how a transmission line will be represented with the help of primary constants R, L, G, C, and from those primary constants how to define and how to derive our secondary constants gamma and Z naught. All these things were learned in our previous class. Now, what we are doing is just we are going to observe what are different parameters which are to be observed to completely analyze a transmission line. So, they are called as the input impedance, reflection coefficient, standing wave ratio, etc. So, now what we do is once again we will go to the previous concepts just in brief and we will continue the topic for this session. So, in our previous topic what we discussed? So, every transmission line can be made with two conductors, it's the two parallel conductors or two coaxial conductors or different types of conductors, and a dielectric will be sandwiched between them. Here this is one conductor and this is another conductor. Between these two conductors a dielectric will be sandwiched. Now, to analyze this transmission line completely, we are supposed to represent this transmission line with its equivalent circuit. So, with its equivalent circuit means in terms of our discrete elements R, L, G, C, but here it is not possible to replace our entire conductor with one discrete element and our entire dielectric with one discrete element. So, what we do is we will take the distributed elements R, L, G, C and we will try to replace our transmission line with the help of that R, L, G, C. Already this topic is very much familiar to us. This is R, L, G and C. So, every conductor can be replaced with a combination of series R and L, and the dielectric can be replaced with a parallel combination of conductance per length, that is a per meter or per length, that what we can say G, and a capacitance per length. So, this is a simple equivalent circuit of our transmission line. So, do not think that as only 1 R, 1 L, 1 G and 1 C will be there. This is a distributed circuit, that what we have. Now, with the help of these four parameters we have defined two more constants, that is propagation constant gamma and characteristic impedance Z naught. Up to this one just we observed the transmission line. Later the transmission line was analyzed for two different conditions. How a lossless line will be observed and what is the condition for that one. As you know, the lossless line will have zero loss, zero attenuation will be there. As the attenuation is 0, clearly you can say that the conductance for our dielectric medium is 0 and the resistance per the conductor what we are considering is also 0. So, R equals to 0, G equals to 0 is the condition for a lossless line, that what you are supposed to remember. Similarly, we have one more type of line that is called as a distortionless line. As a distortion is a parameter which is directly related to the frequency. Right. So, whenever we are observing a distortionless line, so the attenuation factor which is given to the distortionless line is directly proportional to the frequency or independent of the frequency, that what we can say. It is not at all directly proportional, independent of the frequency. And the propagation constant gamma is a combination of alpha and beta, right. That beta is directly proportional to the frequency. So, with this simple concept we have a simple relation R by L is equals to G by C for our distortionless line. Now, just leave all these parts. Not only this one, if we are varying the length of a transmission line, what happens to that? If you are increasing the length, decreasing the length, there is nothing but a variation in the length. You can make that particular transmission line as a pure reactance, a capacitive reactance, an inductive reactance, or a combination of resistance plus reactance. That is one of the things that what we are going to observe. And similarly, if we are adding different loads to the transmission line, what happens to that? If you are short circuiting the transmission line, or if you are open circuit the transmission line, or if you are connecting a perfectly matched line, then what happens to the transmission line? Now we are going to observe. So, with these basic concepts, just we will go to the further topics like input impedance, reflection coefficient, voltage standing wave ratio, and analysis of our transmission line based on different conditions. For such analysis, what we are doing is just we are considering the transmission line as it is. We are not taking its equivalent circuit in terms of RLGC or other things. Just I am taking a transmission line, that a basic transmission line I am considering, and it is characterized with its characteristic impedance gamma, Z naught and propagation constant gamma. This is the basic transmission line that what I am considering. Now I am going to analyze this transmission line. Prior to that analyzation, I require few more parameters. That what will be the input impedance of this transmission line and what is the reflection from the output end, and how much voltage standing wave ratio will be there, or simply standing wave ratio will be there. So within this particular transmission line, for that a little mathematical analysis is required. Just you observe what I am doing. Let us take the length of the transmission line is L, and for our convenience what I am doing is I am considering the length of the transmission line along z axis, that is it is extended from some z is equals to 0 to z is equals to L. That what I am assuming for our convenience, mathematical convenience. Now this is the transmission line, and basically it is characterized with its propagation constant gamma and characteristic impedance Z0. For every transmission line, so what we have to do is just we have to connect one source or generator at the input end and one load at the output end. So the signal which is generated by the generator will propagate through the transmission line, and that will be applied to the load. So whenever it is applied to the load may receive the signal or reject the signal, or the signal may reflected from the end. This all purely depend upon the condition what we have here. Right, now just observe what I am doing. I am connecting a generator at the input end. Let us take a AC voltage VG. VG suffix stands for generator. Here what I am doing is just I am taking a generator voltage V and I am applying at the input end. Let us take the input impedance of that generator is Zg. So a simple generator was connected at the input end for our transmission line, and similarly you can connect the load, right? So at the output end I am connecting a load. Let us take ZL, the load impedance. This L stands for load impedance. So here I am connecting the generator at the input end, load at the output end, and I require few more parameters like the input current. Yet Z is equals to 0. I will assume the current which is going to the transmission line as I0. That is observed at Z is equals to 0. And similarly, if you are observing the voltage exactly at the input, this may be written as V0 at Z is equals to 0. And the voltage across the load, that what I am considering as VL. So here clearly this VL corresponds to the voltage across, L stands for load, and the current which is passing through this load is IL. So these are the parameters that what we require to analyze the parameters like input impedance and some other, right? So just this is the basic structure of our transmission line with the help of our primary constants. Now to get the input impedance equation, so first of all I will define what is input impedance. As all of you know, the input impedance will be calculated at the input end of any circuit, right? Here also the input impedance will be observed at the input end of our transmission line. Here I am denoting that input impedance with Z, so with suffix IN. So IN stands for input. So the impedance which is observed from the input is very, very important. You are observing that one from the input side of our transmission line. Don't take in other direction. If you are observing the input impedance, that's the impedance from input end, then it is said to be the input impedance of our transmission line. So simply what you are supposed to do is you are supposed to observe what will be the voltage at this point and what will be the current at that particular point, and divide the voltage with current, then you will get the input impedance of our transmission line. So here Z in can be simply defined as Vs of Z divided by Is of Z. You may ask us, since the input impedance will be calculated here only? No, the input impedance can be calculated at any location in the transmission line. On the transmission line, at any location the input impedance can be calculated, but the major condition is that you are supposed to view at that particular location, you are supposed to view from the input side at that particular location. As an example, if you are observing input impedance at this location, you can calculate the Z in at some Z is equals to a random location L dash. That is also possible, no problem, right? Not only at this location, you can calculate the input impedance at this location also, then this entire remaining circuit can be taken as load, right? Now what we do is, for our convenience and time being, we will consider the input impedance at this particular location only, that is Zn is equals to Vs of Z divided by Is of Z. Now what are these Vs of Z and Is of Z? Already we derived the equation for our voltage and current in our transmission line. If you recollect them, they are very much similar to the wave propagation equations, right? We have a proper equation for our Vs of Z. What is the equation of Vs of Z? So Vs of Z is equals to V0 plus e power minus gamma Z plus V naught minus e power plus gamma z. A similar equation will be there for current also, right? That is Is of z is equals to I naught plus e power minus gamma z plus I naught minus e power plus gamma z. Two similar equations we have. These two similar equations will gives you an analysis like this. The first parameter, this one and this one, is a constant, is a particular term which is traveling in positive z direction. Along with its propagation constant, you can analyze that one. Similarly, the second term is a wave which is traveling in negative z direction, or the signal which is traveling in negative z direction. The combination of these two will gives us either voltage or current. Now we have to take these two equations to simplify this equation, not as it is, we have to modify them. As I said, you can calculate input impedance here, it's anywhere. So for that, what I do is just I'll take different conditions to analyze these two equations. What are the conditions? At z is equals to 0. So what is this one and this one? At z is equals to L. So what about this and what about this? Here for our derivation at z is equals to 0 is not required. So what I do is directly I will go to, because this derivation is not at all useful to you, I will directly go to the second condition, that at z is equals to L, I will consider this one. Yet z is equals to L, I will modify these equations, just observe. Yet z is equals to L I am considering, right? Yet z is equals to L, what is the voltage across this particular load? That is at z is equals to L, the voltage across this one is VL. So clearly you can take Vs of z, the voltage at that particular location is VL. Similarly, at z is equals to L, what is the current? IL. Is of z can be taken as IL. Now what I do is just I will consider these two parameters and I will substitute z is equals to L here and I will simplify it, right? Just you observe, instead of Vs of z, I will write VL, which is equals to V naught plus will be as it is, that is the magnitude of a forward traveling voltage, that is V naught plus e power minus gamma L, right? Instead of z, I wrote L plus V naught minus e power plus gamma L, that what I wrote. This is one of the equations that what we have. Similarly, IL is equals to I naught plus e power minus gamma L plus I naught minus e power plus gamma L. Just I modified these two equations like this. After that one, what I do is I will try to replace this I naught plus and I naught minus for our future purpose. That just recollect our characteristic impedance relations. In our characteristic impedance, we have a simple relation. That what is that relation? Z naught is equals to V naught plus a forward traveling voltage to the forward traveling current. Or we have one more equation. What is that? The same can be written as minus of V naught minus divided by I naught minus. That is a negatively traveling voltage to the negatively traveling current. So what I do is I will try to replace this I naught plus with V naught plus by Z naught, and I naught minus with minus V naught minus by Z naught. That replacement I am doing here, which is equals to V naught plus by Z naught e power minus gamma L plus, instead of I naught minus, what I can write? Minus V naught minus, that is minus V naught minus by Z naught e power plus gamma L, that I can write. So these are the two equations that what I have from these equations. They are not independent, these two are derived from these two equations. Now once again I will try to modify these two. Just I will simplify them. I don't want to modify, or I don't want to substitute anything, just I will simplify them, right? Just you observe. Now these are the two equations that what we have in our earlier step. Now this also can be simplified as IL Z naught, which is equals to V naught plus e power minus gamma L minus V naught minus e power plus gamma L. Now observe this equation and this equation. From these two equations, exclusively we can obtain V naught plus and V naught minus. Now that is my motto too. My main motto is to get these two parameters. So what you do is just you add them. If you add them and simplify, you will get an exclusive equation for V naught plus the magnitude of the voltage which is traveling in positive Z direction. V naught plus is equals to, what I am doing is I am adding these two. What I will get is 1 by 2 of VL plus Z naught IL, here we have e power minus gamma L, that will becomes e power plus gamma L. Clearly the magnitude of the voltage which is travelling in positive z direction will be like this with these two. And similarly you will get V naught minus also the voltage which is travelling in negative z direction, which is equals to 1 by 2 VL minus Z naught IL e power minus gamma L. These two equations are, or these two particular quantities are required to derive our input impedance. Now once again go to the input impedance equation. What is our input impedance equation? Zn is equals to Vs of Z by Is of Z. Right? Now you can substitute Vs of Z here, that what we have in our earlier step. Is of Z here, that Is of Z also will be modified by substituting I is equals to I plus is equals to V naught plus by Z naught, I minus is equals to minus V naught minus by Z naught. After that you have a simple mathematical manipulation. With that mathematical manipulation you will get a beautiful equation. You are supposed to remember that particular equation only, because all this mathematical analysis is not required to a competitive examination. What you are supposed to do is just you remember the final equation. That equation was derived with the help of these equations. You are supposed to remember these equations because they will be useful for some other applications also, right? Till then, so just you remember these equations. Now what I do is I will try to give you the final equation of our input impedance, and that equation is very much useful to analyze transmission line under different cases. So don't go for the derivation at all, just to remember that final equation. I will give you that equation. So what is the simplified version of that input impedance? Now this is the equation that what we get after simplification of our previous steps. Clearly this equation is a very important equation, as I said, and you are supposed to remember it, and from this equation only we are going to analyze our transmission line under any case, right? Now what is this one? Input impedance is equals to characteristic impedance multiplied with load impedance, where ZL is called as the load impedance, plus Z naught hyperbolic function of the tan H gamma L divided by Z naught plus ZL tan H gamma L. Now once again you can write this gamma as, where gamma is the propagation constant. This can be written as alpha plus J beta. So if the problem is given to calculate the input impedance of any transmission line, we are supposed to observe few things. What is the length of the transmission line? L. What is alpha attenuation constant? What is propagation constant? Beta. And what is the load we are connecting, and what is the characteristic impedance of the transmission line. With the help of these parameters we can calculate also with a simple calculator, right? But here almost all the cases we will consider this propagation constant as just Z beta, that we are treating alpha is equals to 0, that is nothing but a lossless line. So with that analysis, with that simple assumption, the analysis will be easy. So if we are considering alpha also, then the analysis will be little bit difficult. So what I do is, from this point onwards I will take the transmission line as a lossless line. Clearly for a lossless line always alpha is equals to 0, therefore gamma can be written as just Z beta. Now if you substitute tan gamma L here, what you will get is a J beta L, tan hyperbolic function of Z. With your trigonometric relation you can simplify this one as Zn is equals to Z naught multiplied with ZL plus Z naught tan H. Instead of gamma I am writing J beta L, right? L is also there, this is the J beta L. Tan hyperbolic function of any complex number is nothing but J tan X. As an example, if you are taking tan H Jx, then this can be written as J tan X. Remember that point. I am writing that point here, Z naught, this entire thing can be J tan, instead of X what we have here, beta L, divided by, similarly here also this can be written as Z naught plus ZL J tan beta L, or this can be written as JZ naught tan beta L. This can be written as JZL tan beta L. But clearly remember, this equation is applicable if and only if the line is a lossless line. If the line is a lossy line, this only the equation you are supposed to observe. So what I suggest you is, remember this equation for entire transmission line analysis. So if you remember this particular equation, then it is very easy. What is the characteristic of that particular transmission line if you vary the load? Or what is the characteristic of that particular transmission line if you are varying the length of the transmission line? Or so what is the characteristic of that particular transmission line if it is lossless or distortionless, like that? And so you can analyze it for various conditions. So what I suggest you is, once again clearly remember this input impedance equation Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. This is one of the parameters you are supposed to remember. Next we will have one more parameter that is called as reflection coefficient of the transmission line. Now we will discuss what is reflection coefficient. Already this reflection coefficient was observed in our wave propagation. Similarly, here also we have one more reflection coefficient for our transmission line. So what is that reflection coefficient? Let us take a transmission line. This is a simple drawing I am taking. A transmission line is there. Now our main intention is to propagate a signal or transmit a signal from the input end to the output end, right? At the output end we will have one load. So here what I am doing is I am connecting an unknown load to it. Let us take this ZL is an unknown load. Whenever we are connecting an unknown load, there may be a possibility to get the reflection from the load if it is not matched. So what is that particular reflection? Whenever it is unmatched, then the propagating signal in the transmission line may takes reflection from the load end. So this reflection coefficient always will be calculated at the load end only. This is not at all observed at any other point, that whenever we are connecting a load, how much amount of voltage will be reflected from that particular load is said to be the voltage reflection coefficient. Similarly, how much amount of current will be reflected will be taken as current reflection coefficient. So here clearly, whenever some signal is applied here that is traveling in positive z direction, that what I am assuming will travels like this in this direction. If the load is unmatched, then what happens to that one? Definitely it takes reflection in opposite direction. So this is called as a reflected voltage, a reflected current. Now we are supposed to observe how much amount of voltage was reflected or how much amount of current was reflected from the load end. For that we are supposed to take the reflected voltage and incident voltage. Take the ratio of these two. Simply it is said to be the reflection coefficient, and this reflection coefficient is denoted with a symbol gamma, uppercase gamma. So simply gamma can be written as how much voltage was reflected from the load end. So simply that is reflected voltage, and so how much amount of voltage was incident. So it is incident voltage. Now with your analyzation, let me know what is the reflected voltage and incident voltage. That's already we have the equation for our transmission line. For the equation of the voltage for our transmission line, we will have the voltage which is traveling in positive z direction and the voltage which is traveling in negative z direction. That the voltage which is traveling in negative z direction can be taken as reflected voltage. Similarly, the voltage which is traveling in positive z direction can be taken as incident voltage. Directly I am writing those two equations here just to observe. The voltage which is traveling in negative z direction with magnitude V0 minus we have. So V0 minus, apart from this one, a propagation constant e power plus gamma L, that we are observing that one at z is equals to L. At the load end we are observing, that's why I am writing instead of z I am writing L, divided by what is the voltage which is traveling in positive direction, that is nothing but the incident voltage, which is equals to e power minus gamma L. That's why I said you are supposed to remember few equations earlier to this analysis. So now what you are supposed to do is you have to substitute this V0 minus and V0 plus. If you substitute these two, then this is gamma will be simplified. So what is V0 minus? Now recollect that from your previous steps, you will get V0 minus as 1 by 2 VL minus Z0 IL e power minus gamma L. This entire thing was replaced as instead of our V0 minus, that is taken from our previous step, and multiplied with this e power plus gamma L divided by, in the denominator what we have is a V0 plus. Instead of V0 plus, what you can write? 1 by 2 VL plus Z0 IL e power plus gamma L multiplied with e power minus gamma L, that is this term, right? Now simplify this one. If you simplify this one, these two terms will be cancelled, these two terms will be cancelled, half will be cancelled. So the reflection coefficient which is to be observed for the voltage, that's why specifically I will mention this one as the voltage reflection coefficient at the load. So gamma is equals to VL minus Z0 IL divided by VL plus Z0 IL. That what you can write. right? Now what I do is I will take this IL common from both numerator and denominator. The IL will be taken common from both numerator and denominator. Will simplify this equation further, which gives you VL by IL minus Z0 divided by VL by IL plus Z0. What is VL by IL? The voltage at the load divided by the current which is passing through the load is nothing but the simply load impedance ZL, right? So VL by IL can be replaced with ZL. VL by IL can be replaced with ZL. So gamma is equals to just it is ZL minus Z0 divided by ZL plus Z0. That is the final equation you are supposed to remember. So gamma is equals to ZL minus Z0 divided by ZL plus Z0. If you know the load impedance and the characteristic impedance of our transmission line, easily you can calculate this reflection coefficient. And clearly remember, this is not at all a pure real term, this is an imaginary term, right? This can be written as a combination of real and imaginary. Gamma R is a real part, J gamma I is the imaginary part. This will be useful to understand our Smith chart later. For time being, just you remember that. So a reflection coefficient for the voltage is simply ZL minus Z0 divided by ZL plus Z0. You may ask, sir, what is the reflection coefficient current then? As it is, you are supposed to follow the steps. Here consider the current which is flowing in opposite direction or the reverse direction. Consider the current which is travelling in positive z direction. Take the ratio of these two, then that will be the current reflection coefficient. Then what is the relation between the voltage reflection coefficient and current reflection coefficient? Just you observe. What I am doing is I am considering the current reflection coefficient gamma suffix I added to differentiate this gamma and current reflection coefficient. Gamma I is equals to, instead of this one, what you are supposed to consider for current? I naught e power plus gamma L divided by I naught plus e power minus gamma L. Right, don't go for another simplification like this. What I do is directly I will try to simplify this one here itself. Instead of I naught minus, what you can write? V naught minus by minus Z naught you can write. So here what you have is minus V naught minus by Z naught, this term is as it is, plus gamma L divided by, and here I naught plus can be replaced with what? I naught plus can be replaced with V naught plus by Z naught e power minus gamma L. Z naught will be cancelled. Minus of V naught minus e power plus gamma L divided by V naught plus e power minus gamma L. Just you observe this term. This term is very much similar to this term with a negative sign over here, right? So clearly the current reflection coefficient is always opposite to the voltage reflection coefficient. That's why directly I am writing this one. Just you analyze this, easily you can understand that minus V naught minus e power plus gamma L divided by V naught plus e power minus gamma L is nothing but a minus voltage reflection coefficient. So if in the examination the relation between the voltage reflection coefficient and current reflection coefficient is asked, directly you can say that voltage reflection coefficient is equals to negative of current reflection coefficient, or current reflection coefficient is equals to negative of voltage reflection coefficient. And what is the lower value of this reflection coefficient and what is the upper value of this reflection coefficient? Easily you can observe from this equation. ZL minus Z0 divided by ZL plus Z0, in the denominator you have plus. So not at all it is greater than 1. So always it is less than 1 only. The magnitude I am talking, right? It is always less than 1. And what will be the minimum value? The minimum value is always 0. So the magnitude of our reflection coefficient always lies between 0 and 1. Once again, remember that I am talking about the magnitude only. So here I am writing the limit 0 less than or equals to gamma less than or equals to 1. Now if it is 0, easily you can say that there is no reflection. So whenever the reflection coefficient is 0, there is no reflection. Whenever the reflection coefficient is 1, then you can say that 100% reflection is there. So just recollect the probability theory, 1 is the maximum value there, right? So maximum reflection will be there if the value of our gamma is 1, and clearly it is magnitude I am considering, that's why I will put a magnitude sign, right? So this is about our reflection coefficient in any transmission line. Now using this reflection coefficient we are going to go for one more simple parameter, but very important parameter called as voltage standing wave ratio. What is that voltage standing wave ratio? Now this voltage standing wave ratio is also, already we observed a standing wave in our wave propagation. Here also we can observe the voltage standing wave. So what is a voltage standing wave? whenever a transmission line was taken and a signal is applied to this, the signal will be reflected from the load end if it is not matched. Then you have two different types of signals in the transmission line. One is a signal which is traveling in forward direction, another one is a signal which is traveling in negative z direction. It's unwanted direction, right? Now the resultant of these two is said to be the standing wave. Just you imagine one simple example. The water is flowing from one direction and the same amount of water is flowing in another direction or opposite direction. If they hit at some point, the water will not flow. Just the water will stay at that particular location and drops. Similarly, here also, if the wave is traveling in positive direction and the similar type of wave is traveling in negative direction, then the resultant of these two will be standing in that particular transmission line. Then it is said to be a standing wave, right? And if it is voltage wave, then that is said to be a voltage standing wave. Now we are supposed to observe what is the maximum of that particular standing wave and what is the minimum of that particular standing wave. If you take the ratio of the V max to the V minimum of that standing wave, then it is said to be voltage standing wave ratio, and in short it will be taken as VSWR. In some of the examinations, they will give a simple notation to this one as simple S. Just S will be given. S is nothing but the standing wave ratio. Gamma will be given as R reflection coefficient, and for the reflection coefficient sometimes they may use rho also. So as per the problem given, you need to understand what is the parameter given to us, right? Here I will use the notation S for voltage standing wave ratio. How it is defined? Just the ratio of the maximum of our voltage standing wave to the minimum of our voltage standing wave. How you will observe the maximum and minimum of our voltage standing wave? Take the summation of the forward wave and reflected wave, then you may get the maximum voltage. Take the difference between these two, you may get the minimum of the voltage. So simply this can be written as the forward traveling voltage E V0 plus e power minus gamma z. That is the voltage which is traveling in forward direction will be added to the voltage which is traveling in negative z direction, V0 minus e power plus gamma z. Then you may get maximum voltage for the standing wave. Similarly, the difference of these two, that when you will get the minimum, if you are considering a difference as V0 plus e power minus gamma z minus V0 minus e power plus gamma z. So this is a simple equation that what we have to observe this one. Then what I do is just I will manipulate this one by considering or by taking a term common in both numerator and denominator. What I do is this, I will take this V0 plus e power minus z common from both numerator and denominator. If you take this one, what you will get? 1 plus V0 minus e power plus gamma z divided by V0 plus e power minus gamma z, and the denominator now becomes 1 minus V0 minus e power plus gamma z divided by V0 plus e power minus gamma z. Now once observe this particular term, this term is nothing but your reflection coefficient. So this particular entire term can be replaced with reflection coefficient, that is 1 plus gamma divided by 1 minus gamma. Here we are intended to observe the magnitude of S. How much standing wave is there? We don't require any complex quantities. That's why I will consider the magnitude of gamma. Right? This is the relation between standing wave ratio and gamma. And if you substitute gamma here, you will get the particular S in terms of our ZL and Z0 also. No problem. Directly substitute gamma here, you can get the equation for S in terms of ZL and Z0, or else if you want only the relation between S and gamma, you can use this one. This is also one of the important parameters that what you are supposed to remember. So with this one, the voltage standing wave ratio is defined, and there is no concept of current standing wave ratio, because here we are considering only magnitude. If you are considering the current standing wave ratio, let's say as an example, then here you are supposed to substitute minus gamma, right? The minus gamma also gives you the gamma as magnitude. So don't go for that particular different concepts. Don't think like that. There is no current standing wave ratio, only voltage standing wave ratio will be there, and the magnitude is same, right? Now what is the minimum and maximum value for S? By substituting the minimum value of gamma and maximum value of gamma, you can observe that one. What is the minimum value of gamma? 0. So 1 plus 0 divided by 1 minus 0, what you will get is 1. So 1 is the minimum value for our S. one existing, right? So S less than or equals to, what will be the maximum value? What is the maximum magnitude of our gamma? The maximum magnitude of our gamma is 1. If you substitute 1 here, it is infinite. Actually, it is undefined, but you are supposed to take that one as a maximum value for the existing, that is infinite. So always S lies between, the standing wave ratio lies between 1 and infinity. So in the examination, you may have one question like this, that what are the limits of gamma and S? Successively the options will be 1 to 0, 1 0, 1 infinity, 0 1, 1 infinity, 0 1, 0 infinity, 0 1, 1 infinity. Like that, different options will be given. What you are supposed to do is, you are supposed to observe which option is suitable for gamma, and so which limit is suitable for S and which limit is suitable for gamma, and appropriate one you can tick, right? So clearly this standing wave ratio is a very simple one, 1 plus gamma divided by 1 minus gamma, and the limits are, it's a 1 to infinity. It lies between 1 and infinity. So with these three parameters, just we observed three different parameters, the input impedance of our transmission line. We have one lengthy equation. Just you remember that equation, that will be enough. Later we observe the reflection coefficient. So what will be the reflection coefficient at load exactly, and what will be the standing wave? The standing wave will lies in the transmission line, that is not at the load, not at the input end. It always lies within the transmission line. So if it lies within the transmission line, so what is the value of that particular voltage standing wave ratio? These three parameters are very much essential to analyze our transmission lines. Now I will give you one by one. So how to go for analysis of our transmission line in different cases. So we will start with a very simple case, that is short circuit case of our transmission line.